So let's start. So we are going to talk about the topic of chapter 8 in textbook is about the electric fields. So this is the topic we missed, but actually it's this chapter is quite is independent to the other chapters. So let's have a look at what the charge is. So you know the charge, we have the positive charge and negative charge. And then about the forces on the charge, we know that the light charge repel and the unlight charge attract. That's what you know. And then we also have a concept about the conservation of charge. So that is charge can neither be destroyed nor created. So the total amount of charge is unchanged. And also for the charge, we also have a concept we call the quantization of charge. So actually, what does it mean by quantization? Quantization, that means just like the money. In Hong Kong, the smallest amounts of the money, or I mean the real money, okay, is $0.1 or 10 cents. You can't pay any object less than 10 cents. And also all the food or all the thing you can buy in Hong Kong should be the multiple of 10 cents. As the charge, so the smallest amount of charge is E. E is the charge of electron, without the name sign. Or you say the magnitude of the charge of electron. And then all the charge will have the magnitude that is integral multiple of E. Now just there's some exceptional case, except the quarks. So you have learned about the quarks, just like the up quarks and the down quarks. And then you know the amount of the these two charges is not integral multiple of E. So for up quark, the charge is 2/3E. And then for the down quark, the charge is -1/3. But these two particles cannot exist by itself. So they can only exist in form of the baryon or the meson, as what we have talked about it already. So you can just consider every object except except those quarks. They all have the integral multiple of E. So that's the concept of quantization of charge. So but this topic is about the electric field. And then, so we are going to talk about the concept of electric field. So in physics, actually there are many fields. So just like the electric field, magnetic field, and also gravitational field. Actually, what is a field? It's also a question asked in a long question. So what is a field? Field is the region where the object. Now it depends on what you mean. So let's say if I use different color of. So let's say if you're asking about the electric field, so you say the charges. Right? So if you would like to talk about the magnetic field, Then here is the magnet or current. And then if you're talking about the gravitational field, and then this will it will be the mass. So we'll explain. So that's how we define the electromagnetic and gravitational field. So let's say for the electric field, so this is a concept about the region where the charge experience a force. And then many of you may mix up the concept about the electric field and electric field strength. So electric field strength, so this is a measure of the strength of the electric field. Actually, that means it is a magnitude of the electric field. Electric field is a concept, but electric field strength is a quantity to measure the strength or the magnitude of the electric field. So that means how large or how small it is. So in your exam, you need to define it as we have a formula for the electric field strength. And then this is a general formula. So let me write down the formula first. So we use a symbol E for electric field strength. And electric field strength is defined as force over charge. So what does it mean? So let's say, let me draw some random electric field here. So let's say there's a charge here. Here is charge Q. So this charge experiences a force exerted by the electric field. And then you measure the force and then divide by the amount of charge Q here. And that gives you the concept of electric field. So this is, you may ask why we define it as force over charge, but let me write down the definition first. So this is a force per unit positive point charge. So you need to mention there is the unit and positive and point. So this three words is very, very important. You can't miss any of them to get the mark. So this is a force per unit positive point charge. So let's talk about why we define the term like this. Actually, we find that actually the larger the charge, the larger the force. So the larger the charge, the larger the force experienced by the charge placed at the point. Let's say let's say that this point is point P. So let's say this is the point P here. And also we find that the force over Q is a constant at that point. It does not depend on the charge Q. Just like or you rewrite the formula, it will like F equal to QE. And the larger the charge, the larger the force. And then so this is the first important concept here. So second, so why we need to have a word positive? So first, let me use another color. So why we need to use the word positive? So because electric field strength is actually a vector. This is a vector. Actually, it also except the it has magnitude and direction. So the direction of the electric field is actually exactly equal to the direction of the force experienced by the positive charge. So let's say if you see from the diagram, so this is a electric field pointing to almost to right. So if this charge is positive, and you experience the force along the electric field line, so that means it's experiencing a force to the right, and then so does the electric field. Okay, but if you are placing a negative charge here, the negative charge will experience a force that is opposite to the electric field. So that's why we need to have the word positive. Okay, so that's this is an introduction of the concept of electric field and electric field strength. And just you need to remember the definition of these two. Then let's go on. So to represent electric field or to visualize electric field, we will use the electric field lines to show the field strength and also the direction. So that means we use those electric field lines to show the direction and also the magnitude of the electric field. So you need to, so here are some rules to draw the magnetic field lines. Although you need to memorize some common type of electric field lines. So here's, let me give you some rule first. So the rule is, so those field lines, just like this, they're all represented by some lines with arrow there. So field line of a positive charge, positive point charge, a field line always points from positive to negative. So second, so the denser the line, the larger the electric field strength. And I told you that this is a line with arrow. So this arrow shows the direction of the electric field strength is along the tangent of the field lines. Yeah, so we talk about, so this is the three fundamental rule to draw the magnetic field lines. And then actually, there's a few more. So let's give you have a look at few of the field line pattern. So I just copy some photo here. So this one gives you the density of lines in the pattern. So you can see that the charge of A is less than that of B and then less than that of C. And actually in this diagram, actually it shows you that all these three charges are positive charge. And then A, B, C are all positive. Because it's pointing outwards from the charge. So, and then actually this diagram, this one actually shows you most of the few lines that you need to know about it. So first of all, this is a 2 positive point charge. So you need to know about it. And then this one is the two charges placing there. Sorry, let's go through, let's have a look at the 2-point charges. Now for the negative charge, you can see the few lines actually point towards the negative charge. So for the positive charge, the few lines are point away from the positive charge. So if we are placing 2 positive charge together, or placing 2 negative charge together, so because you know light charge will repel. So actually the electric field line will repel also if they are in the same direction. So then you can see that here, actually, it seems like the electric field are repelling each other. And also you can see that there's some point here, there's one point in between here. So this point we call it the neutral point. NEUTRAL. So this is a neutral point. So neutral point is the region where the electric field is 0. Okay. And then if there's one positive charge and one negative charge, because they will attract each other, so does their field lines. So you can see that the field lines actually they just look like they merge together. They merge together. So this is the. So let me talk about the fourth rule. The fourth rule is field lines are perpendicular to the surface. I'm not going to explain it very in deep, but this is very important in exam or in many of the MCs. So if you draw those measure line, this one is actually, this is not a good example here, but this one you can see actually here. So those lines are actually quite perpendicular to the surface. For those measure lines just above, it should be perpendicular to the surface. So let me give you some example in the exam. Just a second. I'm finding a question. So so let's have a look at one of the MCs, past paper MCs. So you need to choose which one give you the correct answer for the field line pattern. So actually you need to use the rule I told you. So first of all, the most important rule is the field line are perpendicular to the surface. So then you actually can then short out 2 answers. So you can short out the answer B and D. So because the surface, this angle is not right angle. So answer A and answer C, they are all perpendicular to the surface. And how can you determine next? The second very important rule is this one. The denser the lines, the larger the electric field strength. So although you don't know about where the electric field strength is larger, but actually we can determine from the diagram. So the closer region, let's say here is these two plates are closer. So the closer the place, it should be the larger the electric field lines. So the larger the electric field strength. So that means the line should be denser here, okay, and then less dense on the top. So therefore, the answer should be A. So because of two reasons, okay. So denser the line, in the lower region, because the electric field strength is larger, and because of the place is closer, okay. So the electric field strength is larger. The second answer is the electric field lines should be perpendicular to the place. Because of these two reasons, therefore we choose the answer A. So then let's go back to so for the case of two parallel plates, so that means this one, this one. So this is very important. We also need to learn about the magnitude. We also need to learn about how to calculate the magnitude of this pattern. So for parallel plate, we will say that the electric field lines are parallel and evenly spaced inside the plate. So inside the plate, it means the region here. So you can see almost the field lines are parallel and evenly spaced. But outside the plate is not even or not parallel. And then what you can notice is, what does it mean? It means that it's evenly spaced. That means the density of the lines are even, are uniform inside the plate. So actually that means the electric field strength is uniform. So that means constant, or you say everywhere the same inside the plate. Actually, there's another rule also. So let me write it down. So the fifth rule here is not that common, but this is about the conductor. The conductor. The electric field strength is zero inside the conductor. So if the electric field strength is zero inside the conductor, that means there should be no field lines. Inside the conductor. So if you draw the diagram, let me show you. Also, let me give you more example of the electric field lines. So let me see. Let me make it smaller. So this is a egg-shaped conductor with charge on the surface, and then the electric field lines inside the egg or inside this object is actually zero. Actually, it's just what you need to memorize. I can't explain more. That's it. Then let's go on. So here is just some question about the electric field lines that you should know about it. And then also let me show you the electric field line of a sphere. Also, let me show you more. So here shows you that it should be 90 degrees, even though the shape look like this one. And then also this one. So you can see inside the metal sphere here on the right hand side, there's no magnetic field lines inside the sphere because there's no magnetic field strength. And then also those magnetic field lines are actually perpendicular to the surface. That's it. So after talking about the shape of the magnetic field line, a magnetic field, and then let's have a look at the question in the textbook. Just one question here. So you need to know a bit, think about which one is positive charge and which one is negative charge. So what you need to use is just a very simple rule. The electric field of the positive charge is pointing outwards. The electric field of the negative charge is pointing inwards. Then that's enough for solving this question. So that means for the part one, both of them should be positive because the electric field lines are pointing outwards the charge. And then the second one, so this one should be positive, but this one is negative. And the last one is that both of them are negative. That's it. Simple.
Sir, why is the field strength stronger at a sharp point?
This is about the sharp point effect. But this is not stated in your textbook. Because actually more charge can stay at the sharp point. This is called sharp point effect. So more charge can stay uh, at the sharp sharp point or at the edge. So just look, just like the let me show you this one. Electric rod. Lightning rod. Light. So just like for the lightning rod, this one. I can't find this one. Just like the lightning rod here. So the lightning rod is a very sharp point, and then those charges will accumulate at a point, accumulate here, here, and here, and then it will, and then it will because most charges will accumulate at a point. Then, because of electrical induction, so you learn about it in IGCSE. You just don't need to know about it in GCE. And then because of there are more charge here, therefore it can attract lighting to hit the rod. This is the principle of the lighting rod. So this one is called a sharp point effect. That's it. Look like this diagram. Look like this one. I think I just flip it up. Let me. So then let's go on. So we didn't accept that formula, except one formula. We haven't talked about any other formula. So let's go to the first formula that you need to know about it. And then so this is about the first formula about the electric field strength. Of parallel plate. So the parallel plate here, it means the opposite charged parallel plate. So that means one plate is negative charge and one plate is positive charge. So let me give you the diagram. It looks like this one. So you can just connect these two plates to a power supply, and then one will become positive charge. The one connected to the positive terminal will become positive charge. The one connected to the negative terminal will be negative charge. And then if we are talking about the small d is the distance between these two plates. And then let's say V is a potential difference across these two plates. Actually, V is also means the potential difference of the power supply. Then the electric field strength of the positive charge parallel plate will be the formula E equal to V over D. Oh, sorry, you haven't talked about the unit of the electric field, but we can derive the unit from this formula. So V is a potential difference. You know the unit of the potential difference is volt. And then distance, we use a meter. So obviously the unit of the electric field strength will be volt per meter. And also there's another unit, very common. So actually we can also use the definition. So this is a definition of the electric field strength. So what I mean by definition is this statement is always true. But this one, E to V over D, only works for the parallel plate. So for the definition of the electric field strength is force over charge. So that will be force, we have the unit Newton, and charge, we have the unit Coulomb. So these two are the unit of the electric field strength. They are equivalent to each other. You can use either one. And then, so let's have some exercise. But we're not going to do all the questions in the textbook. So we almost finished this chapter already. Yeah, almost finished. So question 4 shows arrangement of the parallel plate, each at different voltage. You need to draw the Magpie lines. Now, so for parallel plate, so for question 4, so the larger the high potential, that means the so the electric field lines points from high potential to low potential. So what I mean by high potential, you just look at the volt. So the higher the volt, the higher the potential. So that means inside here it should point from 6 to 2. And what you should draw here is it should be much denser. It should be much denser than the one on the left hand side, because the potential difference here. So potential difference, you need to use 6 minus 2. So the potential difference here is 4 kilowatt, and the potential difference here is 2 kilowatt. So the larger the potential, and then the larger the E, the larger the field strength. So, and then that means you need to draw denser line, the line denser. And then if you look at the between 6 and 0, so 6 is larger than 0, so that means the electric field is also pointing to the right hand side. And this time you need to draw it much more denser because the potential difference is larger. Then that's it. Let's have a look at the question 5. Calculate the electric field strength at a point where the charge 20 millicoulomb experiences a break force. So you know the electric field strength is defined as force over Q. So that means 150 divided by not 20. You need to change the milli to coulomb. So 20 millicoulomb, that means 20 divided by 1000 is 0.02. I think you can get the answer is 7500. Either you use Newton per coulomb or volt per coulomb. That's it.
Sir, are there any other factors of the field line, or is it just voltage?
Factors. So if you look at the check field of a positive charge plate, so it is the there's a formula is the volt
So is it just distance and volt?
yeah, only distance and volt. For question 6, I think it's quite simple. So you just 1000 divided by 40 cm. Of course, you need to change 40 cm to meter. So that means 1000 divided by 0.4. And then if you look at the question 7, question 6, just write down the answer. So it's just 1000 divided by 0.4. I think 2500. The unit is volt per meter or Newton per coulomb. So for question 7, this is a check electron. The charge of electron is given in the formula list. But we remember that electron is never charged. Although the unit, the charge of electron is given as a positive value. And then the electric field, it experiences the electric force like that. And then what's the electric field strength? So if this is not a parallel plate, so you can't use volt per V over D. You need to use the force over Q. Okay. And that means it's H times 10 to the power negative 16 divided by 1.6 times 10 to the power negative 19. Okay, then you can get the answer. I think it's 500 something or 5,000. I think it's 5,000 Newton per coulomb. That's it. So right now the question is quite simple.
Yes, sir, but I thought it says positive charge, right? Or positive unit charge, right?
Yeah. If it is negative, it just means the direction is opposite. But the magnitude is still the same. So
Okay.
then let's go on. So in some of the question, let's say so we have learned about the projectile motion. So let's say if a ball is throwing in the region of the gravitational field, it will follow a parabolic path. That is a projectile motion. And then if the charge is moving inside the field, It will also follow the parabolic. It will also follow a parabolic path. So for the projectile motion in the gravitational field, so the force experienced by the object is constant. And then it has a constant acceleration. And then if you're talking about the projectile motion in the electric field, and then of the parallel plate, okay, parallel plate. So I told you that inside the parallel plate, the electric field is uniform because they are evenly spaced. So what that means? So that means the charge experience. If you look at the formula, F equal QE. Just a second. The force equal to Q times E. The charge does not will not lose when it's traveling inside the electric field, and then the electric field of the parallel plate is constant or uniform. So that means the force is also a constant force. So constant force, and then constant force, that means it's constant acceleration. So that means the movement inside the electric field is actually quite similar to that inside the gravitational field. And then the electron will experience a downward force. Right here, it experiences a downward force. So because the upper plate is negative charge, the lower plate is positive charge. So you can either say the electron is attracted to the positive charged plate, and then so it moves, you experience a force downwards. Or actually, it's better for you to say that the electric field is upwards because it is pointing from the positive charge to negative charge. And then the field lines is upwards, but the electron is negative charge. So it will experience a force that is opposite to the tangent of the field lines. So that means opposite to the direction of the field lines. So that means it is downwards here. So and then it will follow a inside the region of the electric field lines. It is a constant acceleration. So this path here, right here, the path is parabolic. That means a curve. But outside the field, outside the electric field lines, there's no force acting on the electron. So this path is actually a straight line. So that's it. And then, so some of question like that. So let me show you the question. So this is very very famous experiment. We call the oil droplet experiment. So this experiment actually is used to measure the charge of the electron. So they use this experiment to measure the charge of the electron. So they measure the mass of an oil droplet, and then they make it to be positive, negative charge, or positive charge as you like. So and then this is the charge of negative E, okay, in that experiment. And then it adjusts the check field lines. So it adjusts the potential difference across these two parallel plates until the oil droplet is floating in the air, or you just say stationary in the air. So you know this oil droplet will experience a weight, obviously. And then to balance the weight, there should be a upward force. That upward force is actually the electric field, electric force. Okay. So for finding electric force, then we use the formula QE. So that's a definition. And then because this time, this is a parallel plate, so the electric field can be expressed as V over D. So that will be QV over D equal to mg. But if you just write it like that, okay, you choose the wrong answer. So that means you choose the answer that is A, because you need to look at this question. The V here should be, the V in the formula is the potential difference. So you need to get the potential difference of these two plates. So one is positive V, another one is negative V. So you need to find the potential difference. The potential difference will be positive V minus negative V. So it should be 2V here in the formula. 2V. So then the formula will be like this. And then that means the answer should be B, because mg is the weight. You don't need to use it. So actually, let's go back to this experiment. So how it works. So you know, you can measure the mass by electronic bonds or whatever you like. G is, you know, about 9.81. The V can be measured by a voltmeter. So D is the distance between these two plates. You can measure it by ruler or whatever. And Q is the charge of that thing, or if you make it to be negative charge, just losing one electron from the oil droplet, or gain one electron from the oil droplet, then it should be the charge of the electron here. Then you can make use of this experiment to measure charge of the electron. Okay. Then let's have a look of at few of the MCs before. Actually, we finished this chapter already. So let's have a look at few of the MCs. So like this one. So find the ratio of the force of the electron at X and at Y. So to find the force, we use the formula Q times E. So both of them is the electrons. So both of them have the same charge. Okay. So the electric field at X and electric field at Y. Because this is a case of the parallel plate, so you can use the potential difference of X divided by D, and then the V over D, the formula of V over D. So the V at X will be, the electric field at X will be a potential difference across these two plates. So that will be 300 volts. 500 divided by 200. Divided by distance is 2 cm, 0.02. And then Vy will be 200. And then divide by 1 cm, that is 0.01. Then you can find the answer. That's it. So actually in this chapter, the formula is quite simple. Just two formula, Fe or Qe. And also the electric field strength of the parallel plate is V over D. Then that's it. There's no other formula in this chapter. Then let's have a look at one more. Okay. Like this one. So a charged particle moves in the uniform electric field between two parallel metal plates to carry the force. So that means you know the force is QE. Okay. And then which quantity is not required. And you know the E can be written as V over D. So you need the charge. You need the particle charge here. You need the plate separation. You need the potential difference across the plate. That means you don't need the particle speed. That's it. Yeah, actually, that's all for this chapter. And any other question? So any other question? And let's have a look at one more. So find the force acting on the electron at point X. So be reminded that the electron is negative charge. And then if you want to find the force acting on the electron at point X, so first of all, the direction of the magnetic field, as the electric field is pointing downwards. And then it should be tangent to this line. So that means it should be along this direction. This is the direction of the electric field strength. So D actually gives you the direction of the electric field strength. But because this is the electron, it's a negative charge. So the force experienced by the electron should be opposite. So that means it should be B. So that means the answer should be B. So the answer should be B. That's it. So just have a review on what we have learned so far. So we have learned about the concept of the charges. We've learned about the definition of electric field strength, the formula of the electric field strength, or you can say the definition. This one is the definition, and also the rules to draw the electric field lines, and memorize some of the pattern of the electric field lines of the charges. And then we also have learned about the electric field strength of the parallel plate, and also talk about also make use of the formulas we have learned to solve some of the questions in the Oil Droplet Experiment. And then that's it for this chapter. So any other question? No? No question? If no question, then let's dismiss. Okay? Then see you all next Monday in the school. Bye bye. Bye bye.